What I'm going to do is actually tell you about research in progress. And it's the hypothesis that we're working on, the idea or concept that we're working on, begins in the clinic. If a woman comes to the clinic with breast cancer and she's in the age category of 30 to 45 or so, any clinician would begin to be concerned and begin to want to test for the possibility that she has a genetic predisposition to cancer, that there's a mutation in one of the genes that she's carrying that will predispose to cancer, in addition to environmental insults could give rise to cancer at a young age. So cancer at a young age is a tip-off for genetic predispositions. And this has led over the past 20 years now to a search for genes that come to be called tumor suppressor genes, or genes that help prevent cancer. This has led to a search for those genes which give rise to genetic predispositions. And in the case of breast cancer, those genes are ones you know about. BRCA1 and BRCA2 are the two most common genes that predispose to breast cancer. Their frequency depends upon the ethnic groups that you're in. For Ashkenazi Jewish populations, BRCA1 could be as high as 9 or 10%. So 1 in 10 breast cancers could be due to BRCA1, and BRCA2 is fairly high in that ethnic group as well. Then there are some genes which are very rare in the frequency. A gene called PTEN, P-T-E-N, and another one called P53, which I work on, is really found in about 250 or 300 families in the United States, but mutations in those genes can predispose to breast cancer as well. And then over the last 5 or 10 years, people have searched for additional genes. This comes about because we're fairly convinced that there should be additional genes, and we want to know about them so that we can learn how to treat these kinds of cancers. We can learn how to detect them in families. And so there's been a rather intensive search for genetic predispositions to breast cancer in addition to BRCA1 and 2, and this has been a sterile search. We have failed to really find a BRCA3 or other genes which play a role. And it was because of this failure that some bright young people in my research group made another hypothesis. They had a different idea about how a genetic change could bring about a cancer like breast cancer, but you might not find that genetic change in the family. It might only be in a single individual in the family, and yet it would be an inherited change. And so let me explain the hypothesis first, and then tell you just in one sentence at the end the candidate genes that we now have that we found for this hypothesis. When we have an offspring, we make eggs or sperm, and as part of that process, we duplicate the genetic information, DNA, and in duplicating that genetic information, we make mistakes. There's a certain error frequency. So any egg will have 1 or 2 mutations. Most of the time, it's very benign. You never know about it. It makes the offspring slightly different than the parent, and we can track it down with the technologies we have today, so we know we make mistakes. And it's true for sperm, and it's true for eggs. And the hypothesis we have is that while most people in the population, let's say 97% of the population, have an error frequency of making mistakes and passing down genetic information in eggs or sperm at about 0.00001%. It's very, very effective. Some people actually make mistakes at a higher rate. And those people can transmit errors at a higher rate, and sometimes those turn out to be mutations in genes that can give rise to cancer. Right? And so we began to search in the database of cancers the mothers and the fathers of women that developed cancer or women that developed other diseases, because this turns out to be a perfectly general observation for many inherited diseases. We began to search in our databases the mothers and the fathers of women who had breast cancer at a young age, or in fact, a database we're working with on autistic children. We looked at the mothers and the fathers, and we began to see that there were in the collection of women that develop breast cancers at a young age, or in the collection of families that have autistic children, a genetic alteration that's important in the formation of eggs in women, or a genetic alteration that's important in the formation of sperm. So the error rate is up. It's as if you had an automobile, and the automobile was making mistakes because there was a part in the automobile that allowed it to make mistakes, and it could make random mistakes, and occasionally you would get a breast cancer, occasionally you would have an autistic child, occasionally you'd have something else. And we have the tools now to follow this for the first time. And so we have a candidate gene, right, which is involved in the formation of the genetic information in an egg. And we have a candidate gene which is involved in the formation of the genetic information of sperm. And they occur at about 3% in the population, so it's a common change, but 97% of people don't have it, but 3% do, and their offspring have abnormally high error rates that we can measure, and occasionally have breast cancer or autism. And we're tracking this down because the making of DNA in eggs and the making of DNA in sperm are in fact two different processes, and these are two different genes. Right? And these genes are related. They're cousins of the gene I told you about, P53. That's the gene that helps prevent cancer normally, and if it has an unusual error in it, mistakes are made, and this could give rise to a breast cancer. So this could be, these are called maternal effect genes, or paternal effect genes. They're in the parents. They show up in the offspring, not in the parents. And they, in fact, could give us the first hints about the next inherited basis of breast cancer. Thank you.